Great. Well, welcome everybody to this last R user group meeting of term. I'm delighted to welcome our speaker, David Colquhoun, today. And so I'll hand over without any further ado to David.
Yes, it's pronounced Cahoon, actually. Don't blame me. Blame some balmy 11th century Scot who thought the LQ should be silent.
Colquhoun, David Colquhoun. I felt like I was probably pronouncing it wrong, but
everybody does, don't worry. Okay, I'll share screen.
Today I speak to you of war. A war that has pitted statistician against statistician for nearly 100 years. A mathematical conflict that has recently come to the attention of the normal people. And these normal people look on in fear, in horror, but mostly in confusion because they have no idea why we're fighting.
It's a real problem, I think, for statisticians that although they all agree that p-values are not a good measure of what you want to know, they cannot agree on what to replace them with. And this is a problem that's intrigued me since I was an undergraduate, though I only came back to it after retiring, because the time I was retiring, which was 10 years ago, more than 10 years ago now, I'm 86 now, for Christ's sake, this was beginning to bubble up, I think partly because people were beginning to suspect there was a bit of a reproducibility crisis, which of course has become well documented since. So I thought I'd just simulate some t-tests. So I simulated a lot of t-tests with a zero difference. I was just doing a simple students t-test to test the difference between the mean of two independent groups, the simplest thing. Though to this day, you find really quite fierce arguments among statisticians how to test whether that difference is real or whether it's just chance. So I just simulated a lot with zero difference, and then I simulated a lot more with a difference between the means, true difference between the means of one standard deviation. And if you look at the positive tests, which if the p-value comes out close to 0.05, you find that there's not 5% of false positives, but 26%. So this rather astonished me. So I wrote it up in a journal. It was the first volume. It had no impact factor, but it was free to publish in at that time. And to my astonishment, it's now got been downloaded over 300,000 times, and it's got 47 citations. I mean, it's approaching my real work, and it's just naive, really. And at first, I didn't actually understand quite what I was doing. It seemed to me a reasonable thing to simulate, but and still does. But I later got the maths done with a little help and published another paper with theory in it. And more recently, 2019, I published in a proper statistical journal for the first time. So defining the p-value, a lot of people can't do it right, but that is less important perhaps than the fact that even if you do it right, it's very hard to see what it means. If there were actually no effect, if the true difference between means was zero, then the probability of observing a value for the difference equal to or greater than that actually observed is called the p-value. Now that's, even if you get that definition right, it's not obvious what it means, and I'll go into why in a moment. A much better measure, though not how this can be defined is very ambiguous. The false positive risk is the fraction of all positive tests that are false. The difference is quite subtle. Do you want the probability of a positive result when there is nothing, that's the p-value, or the probability that a positive result turns out to be nothing. That has a quite different denominator. It has, the denominator is the number of positive tests. In the first case, it's all tests in the second case, it's all tests in the first case. So they can be very different, those two probabilities, but you've got to be fiendishly careful about how you word things, because the difference between these two things is not obvious, but it's the crux of the matter. I should say that the false positive risk, as I use it now, refers to how to interpret the p-value from a single experiment. It's nothing to do with the problem of multiple comparisons, which I very, very foolishly used the term false discovery rate in that first paper, and that's a term usually used for the case where you do 20 t-tests and you get one significant one and publish it. That which would be, of course, a grave mistake. So what's wrong with the p-value? Well, there's nothing wrong with it. It does what it says. But why isn't it a useful thing to do? Well, the premise is that there's actually no effect. In other words, that the null hypothesis is true. So it can't possibly tell you anything about whether the null hypothesis is true or not, because it's assumed that already. And presumably what you want to know is whether the null hypothesis is true. If there are actually no effect, that implies that the denominator for the probability is the number of cases in which there is no effect, and you don't know that. And why the or greater than bit? Why should you be interested in values that haven't been observed? Well, it's the only way to make it work, a p-value, but it's not necessary, as we'll see. The point is that we need not only a null hypothesis to make any sense of this problem at all. You have to have an alternative hypothesis as well as the null. Knowing that the data are rare when there is no true difference is of little use unless one determines whether or not they are also rare when there is a true difference. That sums it up very nicely. And lastly, of course, the definition makes the error of the transposed conditional. That's what you want, is not the probability of making your observations if the null hypothesis is true. You want the probability of the null hypothesis given your observations. It's like confusing say, is the Pope a Catholic? Well, very probably, you can never be sure. But is a Catholic the Pope? It's very unlikely indeed. It's just, you just can't exchange the order of a conditional probability in that way. But that's exactly what the p-value does. And this is very obvious if you consider the example of screening tests. I read this somewhere about 2010-ish. And this really convinced me that it was a real problem, though it's not an exact analogy, actually. But it became very much in vogue once COVID struck, of course, and there were lots of things, people explaining this. If you test 10,000 people for a disease and 1% of them actually suffer from it, 99% don't have the condition. If the test is a good one with a specificity of 95%, then 95% test negative than those who don't have the condition, and 5% are false positives. So you get 495 false positives. But you can't make any sense of that without looking at the other arm, the alternative hypothesis. If you detect 80%, which is quite good, of people who do have the condition, and that's 80 true positive tests and 20 false negative tests from the 100 people who do have the condition. So you can see that the number of false positives greatly outweighs the number of true positives, simply because there are a lot more negative people in which a test will, if it's positive, will be a false positive. So the proportion of positive tests that are false is 86%. So if you read that the test is 95% specific, it doesn't mean that it's good. Depends entirely on how many people in the population have it. This is what is worrying about the government now. New emphasis on screening, because screening for rare conditions is a very unreliable business. But what persuaded me was its application to tests of statistical significance. If you do over a lifetime 1,000 tests, and just say for the sake of argument that there's 10% of the experiments you do there's a real effect, and in 90% there's no real effect, that would be quite optimistic for screening a lot of new drugs, actually. And you test each of them with a t-test. In these 900 tests where there's no effect, your significance level is cut at the standard 5%, so you get 45 false positives and 855 true negatives. But that's the p-value, of course. But again, you can't make sense of it without looking at an alternative hypothesis. If the power of the test is 80%, which is a standard number that people aim for, but they often don't achieve it, then you get 80 true tests, true positive tests out of the 100 people who 100 tests where there is a real effect. So the false discovery, sorry, that should say false positive risk, damn it. This is an old slide, I haven't changed it. False positive risk is 45 over 45 plus 80. It's 36%, it's not 5%. Now, we'll see in a minute, that's not a perfect analogy to the significance testing problem, and the answer is actually 76% in that case, I would maintain. But it shows that there is a problem. So what are you going to do about it? Well, if you read any biomedical paper, it's littered with p-values. People are going to continue to do that. Most people won't be able to get access to professional statistical advice. And even if they could, the statisticians probably may not agree about the best thing to do. But the only way to stop people claiming a discovery when they observe p is less than 0.05 is to give them an alternative procedure. And a fully Bayesian analysis is probably never going to be adopted. That's the view of the professional statistician Valen Johnson, certainly, and I think it's likely to be the case. There's software that'll do it now, but it makes all sorts of assumptions which are pretty much hidden from the user as a rule, and people don't trust it. But the problem is that if you're asking what's the probability of a hypothesis given the data, which is what you want to know, that is a Bayesian question. There's no escaping that. So at least Bayesians attempt to find an approximate answer to the right question instead of struggling to interpret an exact answer to the wrong question, the second part of that referring to the p-value. So what I proposed, which has not really been met with great enthusiasm among either Bayesians or frequentists, it must be said, but then they don't approve of much. And that is to consider, let's just consider this simple example of the difference between the means of two independent samples. In practice, there are two possible outcomes. You conclude that there's little evidence for there being a real effect. That's not, of course, the same as assuming that the real effect is zero, but it's what you can say. Or you conclude that a real effect probably exists, and that our best estimate of its size is the observed difference between means. And that suggests that the simplest approach is to compare two simple, well-defined hypotheses. The null hypothesis is the difference between means is 0, and you can compare that with the evidence that the difference between the means is the observed value. Now, a proper Bayesian would normally have a distribution of degrees of belief in different values for that difference between means, but I'm just testing it, comparing it with a single value, the observed value. And that doesn't make all that much difference, in fact. But that formulation has several problems. It means that the Bayes factor becomes a likelihood ratio, and that's a simple frequentist thing, which is easy to explain to users. The likelihood ratio in favor of there being a real effect of the observed size is the probability of the observations given the alternative relative to the probability of the observations given the null hypothesis. This isn't a 10, it's 1, 0 to indicate that this is the alternative is in the denominator. If you look at the reciprocal of that, the odds are for the null in favor of the null hypothesis will be called L01. And that's a fairly easy thing to explain, I think, and usually easy to calculate. If you use the odds form of Bayes' theorem, you can just 1 over 1 plus that likelihood ratio will be what I call the FPR50, which is the false positive risk in the case where the prior odds are taken as being 50-50. There's you say that the probability of the effect being real and of the observed size is the same as the probability of it being 0. That's a fairly optimistic assumption, I would say, in many cases. But if that likelihood ratio is modest in size, or even less than 1, then you can't put much confidence in there being a real difference. In fact, I think there's a good argument for just using the likelihood ratio as a judge rather than there's no need to convert it into a posterior probability. But you can if you're happy, and that probability is much closer to what most people think a p-value tells you. If you ask what p-value tells you, if you ask most textbooks what p-value tells you, they'll say it's the probability that you made a mistake in claiming an effect, and it's not that at all. That makes the error of the transposed conditional. Incidentally, if you ask ChatGPT or Galactica that question, it gives you the wrong answer. Artificial intelligence is completely useless as far as I can see for technical questions of this sort. It just copies something off the web. And ChatGPT, it'll give you the references if you ask it. It said, what does a p-value mean? I typed in, and please give sources, and it gave us two websites, which are not very reliable ones. Awful. Of course, if the hypothesis that you're testing is an implausible one, so that the prior odds are less than 50-50, then the false positive risk will be bigger. So what does this look like? Well, there's a subtlety which most people have overlooked, that there are two different ways in which you can calculate the likelihood ratio. That's made very obvious when you do the simulations. because it depends how you define a positive result. If you define a positive result when you're doing the simulations of 100,000 t-tests, 100,000 t-tests, incidentally, in R took about 3 minutes on my 7-year-old laptop. It's remarkably quick. If you take every value that comes out with a result comes out with p less than 0.05 as a positive result, then you get the same answer as you do from that tree diagram. If you observe p equals 0.05 in a well-powered experiment, there'd be 36% of values which are false positives. But because you're doing a comparative test, or should be doing, comparing a null hypothesis with an alternative hypothesis, you don't have to count the values that you don't observe. You can just take the relative probabilities of, if you've observed p equals 0.049, you aren't interested in tests that come out with numbers much smaller than that. You're only interested in tests that come out with p equals 0.049, like the one you've observed. So if you count as a positive test one that comes out with p equal 0.049, or since I was doing it by simulations, you had to take a narrow band around that, say 0.045 to 0.05, to get a decent number, then you get a much higher false positive risk. And that's what I think you should do. This has been known, this distinction has been known for a long time, at least probably since the 1930s. But it hasn't got a name, so I just call it the p equals approach or the p less than approach. So let's just look at this bottom right-hand graph. That's the false positive risk, the FPR50 as I call it, when the prior probability of there being a real effect is 0.5. This is the observed p-value along the bottom. That's 0.05 there. And this dashed red line is the line of equality. So if the p-value is equal to the false positive risk, it would lie on that red line. You can see that it's always above the red line. Though if you use the p less than method for calculating the likelihood ratio, it'd be quite close around the value matters, about 6% rather than 5%. But if you use the p equals method, which is the appropriate one, I think, then you get 26%, as I did in the simulations. These are calculated curves. So if you look at the false positive risk as a function of the number per sample, then you get curves that look like this. And this is surprised people at first, surprised me at first, but then I went into it and I found out it makes sense. This is with 4 observations per sample up to 64. But because the number varies, the power of the test varies enormously. If you observe p equals 0.05, then with 16 observations, you get a power of 78%, which is about the standard sort of value. In principle, you can get a false positive risk slightly lower than 26% by using a smaller sample. That seems paradoxical, but it's a small effect, so it doesn't is not of any great practical importance. What is more surprising is that as the sample size increases, the false positive risk increases toward 1. And that seems silly. It's the opposite way to the way that a frequentist test behaves. It's called the Jeffreys-Lindley phenomenon. It's been known for donkey's years. And it makes perfect sense when you come to think of it, because here you've got a sample size of 64, the power in that case would be 0.9999, which is enormous and not achieved in practice except in some genome-wide screening things, which is another problem. But what that means is that almost all the p-values, if there's a real effect, would be tiny. So it would be very rare in that case to observe a p-value as big as 0.05. And that's why if you had observed p equals 0.05, despite having a hugely powerful experiment, that would be suspicious and it would probably be a false positive. And the same thing happens if you observe other p-values, it just happens much later. So, having got the exact calculations, of course, the R programs are all provided with the paper in the proper way, but not many people download them, I don't think. So I thought I'd better make a shiny app, and that was a bit of a saga. I read the instructions, but it wasn't working right. So I put it on Twitter, where I had quite a few followers before Musk took it over, and asked for some help, and I immediately got it. This is the wonderful thing about R. People are very, very helpful. And so we got it working, and it was published with the link fprcalc.ucl.ac.uk. It was set up on the UCL server by a very helpful lady called Raquel Alegre, who's now sadly left. But then UCL shut it down after the publication. This is infuriating. It's happened to me lots of times. We published a link to our resources for many years on the UCL pharmacology department server. Then the pharmacology department got shut down and every link in every paper was broken. Furthermore, what's more annoying is that the way that a Shiny server is set up means you can't redirect to it. Oh, you can only redirect to a page which leads to it, but that didn't exist on the Eindhoven server, which came to my rescue when the UCL server was no longer functional. So that was very annoying. But I, in the end, asked the people at Positive Internet. They're the people who host my blog. They're wonderful. They use 100% green electricity, and they're fond of skeptics. So the time when I got onto them was after my blog had been thrown off the UCL server by Malcolm Grant, because I'd said that this was a quack medicine thing. A herbalist had said that red clover is a blood cleanser, and I said that's just gobbledygook, of course. And they got very cross and started harassing the provost and people like that. So they instead of defending me, UCL threw me off the server. But the people at Positive Internet, who also host Ben Goldacre's server, said that's terrible, we'll do. So I asked someone there what to do, and they came up with this idea. They set up a little thing on the server where my blog is, which just embeds the Eindhoven server on a web page, and that just works perfectly. Well, not quite perfectly, because it doesn't resize on a mobile phone the way it should, but otherwise it's good. So I can start it. This is just running locally now, but I can run it fprcalc.ucl.ac.uk. That's the one coming from Eindhoven via that embedding link on on the positive internet. So everything happens so fast on the internet now, you can't really tell the difference. With all those intermediate steps involved, I thought it might interest people who also have trouble with UCL being dozy about setting up shiny servers. So there are three options in this. There are three variables, and given two of them, you can calculate the other one. You can calculate the false positive risk given a p-value and the prior probability. The prior probability of there being a real effect. Or you can calculate the p-value for a given false positive risk and prior, or you can calculate the prior for a given false positive risk and p-value. The data here are represented just by the p-value, or equivalently by the value of students t. So the default is option 3. I think it would be option 1, but I changed the default later. So if you observe p equals 0.05, you reckon there's a 50% probability of there being a real effect. Before you did the experiment, you got 16 in each sample, and then effect size as a multiple of the standard deviation. Normalized effect size is 1. That's what psychologists would call a big effect, and electrophysiologists would call a small effect. Then you can see the output here. There's a 26% false positive risk, FPR 50. And if you make the prior probability only 0.1, then it shoots up to 76% false positive risk. Base that with 0.5. You can see that the likelihood ratio is only about 2.8. In other words, your data only are less than or about 3 times more likely under the alternative hypothesis than they are under the null hypothesis. And 3 times more likely is not much compared with the 19-to-1 odds you'd expect on the basis of the p-value. You'd expect incorrectly, because that's not what the p-value means. But if you think that 0.05 is a reasonable chance of being wrong, then 26% is much bigger than that. And a likelihood ratio of about 3 is not very good. One on 1 plus 2.7 is 26%, I said earlier. So if you go on to radio button 1, then these observed values change to false, the observed p-value, and the false positive risk which you want. This is the so-called reverse Bayes method, because the problem with Bayes' theorem, of course, is knowing what the prior probabilities are. But you can reverse it, and if you can specify what false positive risk you want, you can calculate what the prior probability should be in a simple case like this, not in the general case. And what it gives you, a prior probability of 87%. You'd have to be almost 90% sure there was a real effect before you'd done the experiment in order for 0.05 to be a convincing result, if you define a convincing result as a false positive risk of 5%. And of course, if you went to a journal editor and said, yes, I've got a significant result, and in order to calculate that, I have had to assume that I'm almost 90% sure there was a real effect before the experiment, you'd just be laughed out of court. Of course, most journals to this day, almost all journals, still allow you to use 0.05 as a criterion for statistical significance, not knowing that it implies that. Option 2 allows you to calculate a p-value for a given false positive risk and prior. So if you want a false positive risk of 5% and the prior is 0.5, then you need a p-value of 0.008, which is much smaller than you might, or most people might expect. So now I don't need to go through all these because these are all the same thing. That's the reverse Bayes. This is calculating the p-value for a false positive risk of 0.5%. This is, sorry, 5%. This is a table from one of the papers, the 2017 Royal Society Open Science one. You can see this false positive risk for the prior, that's for the prior 50-50. 27% if you observe p equals 0.05. That's 1 on 1 plus 2.8. 1 on 1 plus 6.1 is 0.14. If you observe 0.05, you see you have to get down to 0.0, observing p equals 0.005 before the false positive risk falls below 5%. And if you have a prior of only 10%, in other words, you think it's fairly unlikely that your hypothesis is true, then even when you've observed p equals 0.001, the false positive risk is still bigger than 5%. So in other words, extraordinary results require extraordinary evidence as the time. This is an example, but I've running out of time rapidly, so I won't do it in any detail. This was a thing from the journal Science, which is just nonsense, I think. It's a big study of transcranial electromagnetic stimulation. It was mostly about functional magnetic resonance images, but clearly the referees had said you got to have something functional in. And they did some quick tests of memory and got p equals 0.043, so it sailed in and got plugged onto it, a big metric score. In order to find the sample size, you had to dig into the supplementary material. And when you did that, you find, using that calculator, that the false positive risk, even assuming that zapping your brain with electricity was going to improve your memory, was as likely as not. The false positive risk comes out to be 18% in that case, or the likelihood ratio of 4.5. So I think you should still give the p-value, if only because that's from the p-value you can calculate the false positive risk. But you should give also a number which is some measure of the false positive risk. You can't do it exactly. There are too many assumptions. You don't need it exactly. A false positive risk of 20% or 40%, who cares? I mean, they're essentially the same in their consequences. So you can say that the result implied a false positive risk of at least 18%, so the result is no more than suggestive. Or you can say that in order to get a false positive risk of 0.05, you'd had to assume a prior probability of 80% that there was a real effect. That's the reverse Bayes method. So again, you'd have to assume that the result was no more than suggestive. Or if you assume prior odds of 1, the FPR 50, to get that down to 0.05, you'd have to observe a p-value of 0.0043, not 0.043. So again, the result is no more than suggestive. But you don't have to use Bayes at all. You can simply say that the observations are 4.5 to 1 more probable under the hypothesis that the true effect is the observed size, as it is under the hypothesis that the true effect size is 0. And 4.5 to 1 is much less impressive than the odds of 19 to 1, which you might mistakenly infer from p equals 0.05. P is less than 0.05. So the result is only suggestive, and that is the gist of what I've got to say. I might it boils down to this lovely quotation from Eric Wagenmakers again. So I think, rather reluctantly, despite the huge contributions that Ronald Fisher made to statistics, there's an element of truth in the conclusions of physicist Robert Matthews. The plain fact is that 70 years ago, Ronald Fisher gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. It's time to pull the plug. I think I agree with that.
Well, thanks very much, David. If people feel free to turn your cameras on. If anyone's got a question, just raise your hand. I thought I might start by saying, for the effect size, do you have any advice on, or maybe you could say a little bit more about determining what the effect size is that you put into your calculations?
Well, the normal effect, it's a normalized effect size that you have to enter in. That's the actual effect size divided by the standard deviation, the error standard deviation. And that's easy to calculate that wrongly, actually. It's not the standard error, it's the standard deviation. That's a thing which is called Cohen's D, I think, by psychologists, but by nobody else. And it's not generally a very helpful thing to quote, because from the experimentalist point of view, what you want to know is the absolute effect size, not the normalized effect size. But you want to know its standard error as well, so you'll have a standard deviation there, and you can calculate the normalized effect size. And that's what you have to plug into the calculations.
Okay. Could you maybe say something about your experience making a Shiny app? Maybe there's some people here who haven't done one before, and if you've got any advice or thoughts.
Yes, it's well, if you're used to programming for Windows, I suppose it comes naturally, but it's very unnatural to the person who spent most of their life writing Fortran programs where things just go sequentially. The circular nature of a Windows program or a Shiny program is quite difficult to get hold of. At least I found it so. We did get our analysis programs where we hired somebody to write our analysis programs for single molecules as a Windows program, but she did eventually manage it. It took a long time. I've forgotten now, unfortunately, what the mistake was that I made, which had to get sorted out with help from somebody on the web. A chap called Colin Longstaff worked for the MRC standards unit, what used to be their biological standards unit. It was something to do with the fact that those 3 radio buttons, they go to 3 different pages, and it was to do with the naming of those pages. But by and large, I just found examples on the web and followed them. and till I got stuck, and then I asked, and then somebody told me what to do.
Makes sense. Kimberly, you've got a question?
Yeah, my question is, you said that it's difficult to come up with the priors sometimes. So to look into the transcranial study, you chose a prior of 0.5 in your R app. So is that a recognized strategy? So if you're not sure what you should put in as your prior, is it accepted to just put in 0.5? So basically you're being pragmatic and saying, I've got an open mind.
I think 0.5 is the nearest you can come to declaring indifference. Yes, that's arguable.
But normally you will always have a hypothesis, won't you? So I would have thought it was like you're always going to be a little bit more than 0.5 for most scientific hypothesis-driven research. But is 0.5 just more honest? So if you're not really sure, it's better to go with 0.5.
Well, in some cases, there's good reason to think it's a lot less than 0.5. If you're scanning new drugs, the success rate is usually well under 10%. So, and if you're testing a homeopathic drug where the treatment is actually identical with the placebo, then the prior should be indefinitely small, clearly, since if the trial thing is identical with the placebo, then the false positive risk is going to be 100% always.
But for example, like in my own research, normally what I do is I take hypotheses from animal models. So I look in animal work, they show an effect in animals, like in a rat, and then I try and demonstrate if that holds true for humans as well. So normally I think that I have quite strong priors just in terms of, just common sense wise. But I wouldn't know how much higher than 0.5 to go. So
no, one never does. That's the trouble. Well, you can use the reverse Bayes, and if you're satisfied with a false positive risk of 0.05, you can calculate the prior you need to get there. And if it's 90%, then you have to persuade an editor that you're right to assume that. But good luck doing that, I say.
Okay, thank you very much.
Some people, there is a school among statisticians that says the null hypothesis is never true exactly. Well, I think it can be if you just give two identical pills. And but I think that objection is pretty pedantic, actually, because there are many cases in which the null hypothesis is near as damn it true. And you can say, well, you can say the null hypothesis should be the smallest effect size that's of interest, but these things only make a fairly marginal difference to the calculations. And of course, a Bayesian might have a prior which was a normal distribution centered on the zero, but I don't like that at all. It gives very little weight to the null hypothesis, and I think most bright ideas turn out to be wrong, and the null hypothesis should really have quite a lot of weight.
Evan?
Your R Shiny app elegantly shows the problems with claiming statistical significance in one's research. I wonder whether you would advise for the practicing researcher whether they really ought to just report exploratory investigations, looking for trends and correlations or relationships to generate further hypotheses, rather than claiming statistical significance, as you've outlined.
No, I think it's very reasonable to try to tell whether your results are just a chance or not. It's just that people are absurdly over-optimistic about it if they just use p-values. So I think they should continue to give p-values in confidence intervals, because people are familiar with them, even if most people don't understand them. What they actually mean. But they should also give another number, which is some measure of the false positive risk. I mean, I quite like mine, but there are others. In fact, there's a much simpler one based on the minimum Bayes factor, minimum likelihood ratio, which is just, you just calculate it from the p-value alone. You don't have to have the other things. And that gives a similar answer. Well, it gives a slightly more pessimistic answer. 29% false positive risk for if you observe p equals 0.05, whereas mine gives 26. That's essentially the same. But
Thank you.
I think continue to do as now, but also give one extra number, which is some rough estimate of the false positive risk, I would say.
Thank you very much.
I'm conscious that we've run over, so I understand that people in the room might need to move out if there's other people coming in. I'll just take one more question from Salma for anyone who's got a few minutes to stick around. But in the meantime, just beforehand, I'd like to thank David again. Several people have said how much they appreciated the talk in the chat, and I will be circulating a link to his YouTube channel and the talk. Okay, over to Salma.
Thank you very much. I have just a quick question because I never come across any paper which talks about the p-values and it's significant and insignificant. And it's really good that I'm doing the analysis on the precipitation. And when I'm basically looking about the rainfall trend, whether there is any significant again and non-significant, but it's good that I come across this. I just wanted to ask, like, what is the best way, for example, because we used like through all over these years about the p-value, the significant and insignificant, then what is the best way to express, for example, the rainfall trend if it says anything related to p-value? I'm trying to avoid the word significance here.
Yes, well, I was, along with 800 other people, I think, signed the letter saying the terms significant and insignificant should be not used, just because that wasn't saying that p-value shouldn't be used. It was widely misunderstood, that letter. It was just saying that the sharp threshold of 0.05 shouldn't be used. You just say p equals 0.001 or p equals 0.049. And that, of course, assumes that people know what it means, which they don't, by and large. But what I'm saying is it would be helpful if you could say we've observed p equals 0.043, and that corresponds to a false positive risk 50 of 20%. And that you can choose your, it's then up to you. It shows that the uncertainty is much bigger than you might expect from p equals 0.05. But it's not an exact statement, but then you can't make an exact statement. Science is hard. Inductive inference is hard. But if you give that extra number, I think I'm afraid that the large number of citations for that first paper, apart from the fact that it was simulation and not much maths in it, which always helps the citations, is that it's cited by everybody who doesn't want to find an effect. Which, of course, is just as bad as being cited by everybody who does want to find an effect. But you can't do much about that. What I can't do is persuade any journal editor to take notice of these ideas. I spoke to the chair of the consortium of European pharmacological journals, representing a lot of journals. And he said we couldn't do that, it would harm our impact factor. Now, that's not deeply corrupt. What the hell is? I mean, this is not how you decide how to offer statistical advice. I really think the publishing industry is such a disgrace. And it's also unnecessary. We could all just publish on the web and open the comments. And there'd be no more rubbish about than there is at the moment. There'd be a lot of rubbish about, but no more than there is already. And it'd be a great deal cheaper.
Great. Well, thanks again for the talk, David. Would you be happy to send me your slides?
Yes.
That I could circulate.
I can send them, yes.
All right. Well, great. I'll see everyone in the new year.
Thank you.